Hello everyone, welcome back. In this video, we'll be taking a look at limit superior and limit inferior. So, limit superior is also called lim sup. So, what it basically means, it is the largest subsequential limit. So, what does that mean? So, if a sequence a n has various subsequences such as b and k, c and k, d and k, e and k, and each of these subsequence have a limit. For example, b and k tends to b, c and k tends to c, d and k tends to d, e and k tends to e. So the limit superior or lim sup is basically the largest of this b or c or d or e. So lim sup is basically the largest limit of all the limits of the subsequences of the sequence. So, or it also has another definition. So this is the simple definition, it's easy to understand. So the more complicated one is, so if an is a bounded sequence, so this is another way of saying what we just said before, which is it's the largest limit of all the subsequences. So the another way of saying it is, if an is a bounded sequence, then define Sn. So Sn is a new sequence, and we're defining Sn as a supremum of Ak with k greater than or equal to n, and lim sup of lim superior or lim sup is the limit of this new sequence Sn, which we defined as the supremum of Ak. So what does this basically mean? So let's take a look at this like graphically to get a clear idea of what this means. So consider this sequence which goes like this, right? So let's now try to build the sequence Sn to see what's really happening. So Sn is defined as the supremum of Ak. I'm sorry, this should be Ak with k being greater than or equal to n. So this is the sequence, this yellow sequence is the sequence An. So Sn is basically, when we take AK, we take A as 1. When we take that, so let me just explain what this means in a second. So this is the supremum of this sequence An right now. So this is the supremum, this is S1, right? So since now we have S1, this is the first term of the sequence Sn. So Sn, we have S1, right? Let me write it with a small room. So this sequence Sn has first term S1, which is the supremum. So this is the first term, remember, this is the second term, this is the third term, fourth term, fifth, sixth, seventh, and so on and so forth. So Sn, the first term of the sequence Sn, which is S1, is the supremum of all the terms of the sequence. And the second term will be when we throw out this first term. Remember this first term A1. After we get the supremum S1, since we define it as k being greater than or equal to n, so we now throw out the first term and only consider the next. We only consider the terms from A2 onwards. So from A2 onwards, the supremum is now this. This is S2. After we do that, we now throw out the first and the second terms, and now we consider the supremum again of the remaining terms. Note that these are the remaining terms. These ones right here are the remaining terms. Now we consider the supremum again of the remaining terms, and we get remember that supremum is the least upper bound, it's the least upper bound, and we get this term A3 is the least upper bound. So we get this as S3. And now after we get S3, we throw away the first, second, and third terms, and now only consider these remaining terms. And the supremum of the remaining terms is where A4 is. So we draw that as here, S4. So that's how we build the sequence Sn. So if you have noticed something, we get that Sn is a decreasing sequence. It's a decreasing sequence. S1 is greater than S2, and S2 is greater than S3, and S3 is greater than S4. So we get that at best that S1, that the succeeding term is either less than or equal to the previous term. So since this is a decreasing sequence, and remember that an, we said an is a bounded sequence right here. We said an is a bounded sequence. So since this is a decreasing sequence that is bounded, and by monotone convergence theorem, it converges, the sequence Sn converges to some limit L, and this limit L is called the lim sup, the limit superior of the original sequence an, or it's also known as the limit of this sequence Sn. So the limit of this sequence Sn is the same as the lim sup of an. So that's what limit superior basically means. Now limit inferior is exactly the same, but just with some few differences. So limits inferior, the simple definition is the smallest subsequential limit. So remember that limit superior was when we had to see different subsequences for the same sequence, and the limit superior is the largest limit value, is the largest value of the limits of all the subsequences, whereas limit inferior is the smallest one. And similarly we have that uh, the second definition, or alternatively, if we have an to be a bounded sequence and in to be the infimum of the set ak, then lim_inf of an is the limit of this sequence in. So if we consider that same sequence as we did before, remember that we had a sequence like this when we consider for lim sup. So if we consider the lim_inf of this, so the infimum of all these terms, so the sequence in, so I1 will be this, and then we throw away the last term, then consider the infimum of the rest of the terms, and so the infimum of the rest of the terms will be this. So this is I1, so this is I2. So we get that the infimum, the sequence in is increasing. I1 is less than or equal to I2, and I2 is less than or equal to I3 as we're going up and up. So we get this sequence in is bounded and it's increasing. So it's by monotone convergence theorem, it converges, in converges to some limit L, and this L is the lim_inf of an, or it's the limit of this new sequence in. So let's take a look at some examples on how to calculate lim_sup and lim_inf. So there are various tricks to consider when you calculate lim_sup and lim_inf. But the one I basically use is, for example, if you have the sequence an as -1 to the power n, and n -1 to the power n plus 8 to the n plus 1 over n plus 1. So what I basically do is I see the maximum value, max, that the limit. So the max. Remember that lim_sup and lim_inf will only be finite numbers if the sequence an is bounded. They'll only be finite if an is bounded. So what I try to do is, now we know this sequence, so what I try to do is I try to find the maximum value that the sequence can be and the minimum value the sequence can be. So in this case the maximum is when, since -1 to the power n oscillates between 1, -1, 1, -1, the maximum value the sequence can be is when it is this, when it's 1, when n is even. So when n is even, this will become -1 to the power n will just be 1, and we get n plus 8 over n plus 1. And the minimum will be when it's -1, when n is odd. So we get that minus n plus 8 over n plus 1. Now all I do is just calculate the limit of this and the limit of this, which we know is pretty easy. The limit of this is 1, so this is the lim_sup. The limit of this is the lim inf, which is -1, and we're done. So the same goes for part B. We know that cos oscillates is between 1 and -1. So it never goes greater than 1 and it never goes less than 1. So the maximum is when this will be 3 plus 1, and the minimum is when cos will be -1, when it will be 3 minus 1. And in this case, we have 4 and we have 2. So the lim sup is just 4, and lim inf is 2, and we're done. So for part C, we have an interesting sequence which is not bounded. Remember the previous two sequences where we could find a maximum and a minimum, whereas for this sequence we really can't. So therefore, in this sequence, the lim sup and lim inf don't exist. They don't really exist because because over here we could find subsequence. This is a subsequence and this is a subsequence, and over here part B we could find a subsequence and a subsequence, but in part C we cannot. So let's go ahead and prove some theorems involving lim sup and lim inf. So firstly, the first theorem is that the lim inf of an is equal to the lim sup of an if and only if limit of an is equal to L. So if the lim inf of an is equal to the lim sup of an and both of them have the same value L, then the limit of the original sequence an, the limit of an is also L. And so this is let's go about with the proof of this. And remember, this is a if and only if statement, so we have to prove both directions. So first I'm going to prove, okay, let's prove the harder direction first, the forward direction. The second direction is pretty easy. So when we're doing the first direction, we can assume, right? Now let's show, okay, the first direction is when we assume lim sup of an is equal to lim inf of an is equal to L. Then we have to prove the limit of an is also equal to L as well. Right, okay, this is the easy direction. I think the hard direction will be the reverse direction, but I don't know about that. Let's see. So let epsilon be greater than 0. Then there exists an n. Because we know we can assume this, there exists n such that Sn minus L is less than epsilon. Remember that lim sup of an is equal to the limit of the sequence Sn, and we define Sn as and we know what Sn is as we defined it in the previous part. And In minus L is less than epsilon for all n greater than or equal to n. And because we know that In is always less than or equal to An, it'll never be greater than An. At best, it'll be equal to An, but it'll always be less than or equal to An. And An is always less than or equal to Sn. And we know that In tends to L and Sn tends to L. So I hope you guys are seeing this. By squeeze theorem, since an is being squeezed by both these sequences which have the same limit, an also tends to L. And we're done with part one of the proof. So this was the easy direction. Let's now prove the harder direction. So whenever you're doing if and only if proofs, one direction will always be pretty easy and the other direction will be a bit more challenging. So when we're doing the other direction, we have to show that we can assume limit I hope I don't run out of room here. The limit of an is equal to L, and we need to show that lim sup of an, which is equal to limit of the sequence Sn, is equal to L as well. The case for lim inf is also done very similarly. You guys can just do it on your own or just copy out this proof and make some few changes um, to do the proof of lim inf. So let's show that if limit of an is equal to L, the limit of the lim sup of an is equal to L, and the proof of lim inf is done similarly. So let epsilon be greater than 0. Then because limit of an is equal to L, there exists, we know this is true, then we can write this as there exists n such that an minus L is less than epsilon for all n greater than or equal to n. So this basically means, so because this can be rewritten as L minus epsilon less than an less than L plus epsilon. Right. So what next? So this means L minus epsilon and L plus epsilon are upper bounds and lower bounds for the set. L minus epsilon and L plus epsilon are lower and upper bounds respectively for the set. So this is the set of the terms of the sequence an plus 1, an plus 2. So the sequence an is basically bounded by this L plus epsilon and L minus epsilon. At least some few terms of this so at least the terms at the ending of the sequence are bounded by L minus epsilon and L plus epsilon. So the set of terms of this sequence are bounded by L minus epsilon and L plus epsilon. So it follows that L minus epsilon is less than or equal to the sequence Sn also, and L plus epsilon, because Sn is derived from the sequence An for all n greater than or equal to n. So let S be the limit of Sn. So from this we get that since S is the limit of Sn and we know it exists, it follows that L minus epsilon, since L minus epsilon is less than or equal to Sn, which is less than or equal to L plus epsilon, L minus epsilon is also equal to the limit of Sn, which is equal to S, which is less than or equal to L plus epsilon. This can be rewritten as L minus S is less than epsilon, which implies L is equal to S, because let me explain why. Because L minus epsilon is less than epsilon, and remember that epsilon is really small. It's always in the terms of 0.00000 trillion zeros and then a 1. So we basically get that the difference between these two is less than 0.000000001. So that basically implies that L is equal to S, and that's what we needed to show. We need to show that lim sup of an, which is the limit of the sequence Sn, is equal to L, and we're done with the proof. So let's take a look at one last theorem before we end the video. So it says that prove that the lim inf of an is always less than or equal to lim sup of an. Well, now this is a pretty easy proof. So note that we know Sn is equal to the supremum. I'm going to state this sequence, define this sequence once more. K is greater than or equal to n, and In is equal to infimum, ak of k being less than or equal to n. And the limit of Sn is equal to the lim sup of an, and the limit of in is equal to the lim inf of an. And then for each, and so now this is the proof. I'm writing out more formally. We have Sn being greater than or equal to In, or let me write it this way, In always being less than or equal to Sn. And so by the order limit theorem, we have the limit of In will also be less than or equal to the limit of Sn, and limit of In, remember, is the lim inf of An, which is being less than or equal to lim sup of An. And that's exactly what we needed to show. And we're done with the proof. So hope you guys have enjoyed this video. See you next time.